Well, see, there are few more important points left in this first group. So one of them is the solution of metal in liquid ammonia. So see, all of you are knowing that this ammonia is a non-aqueous solvent, and self-ionization of ammonia is taking place like this: NH4 plus NH2 minus. So this is the self-ionization of ammonia in pure state, when ammonia is taken in pure state. Okay. Suppose that if you are taking a metal of first group or even few metals of second group also, if you take this metal and liquid ammonia, pure ammonia, but if there is some impurity in that metal or some catalyst or impurity, catalyst like iron, or some impurity is there, so what is happening? Immediately this metal M of the first group that will react with this and form the MNH2 and hydrogen, right? MNH2 and hydrogen, half of H2. This will form, right? There are very simple mechanism for this. Metal will have low ionization energy, as all of you are knowing, so this will form M plus this electron, and this electron NH2H. So this dissociation, so H plus, and this electron is accepted by this H plus to convert hydrogen, and NH2 minus that will stabilize with this. So this is the simple reaction that takes place when you take a metal with some impurity or some catalyst like iron is there. Okay, if there is no impurity, if this metal is free from impurity, it is pure, right? In pure state, this metal M, when we are taking with ammonia, so what is happening here? This time this MNH2 is not formed immediately, and what will happen? M plus ion and electron, this ionization process, and this M plus ions are surrounded by NH2 minus basically, and this electron is surrounded by NH4 plus, right? So this process is called solvation, and this is called solvated electron, right? So whenever you take this pure metal in pure ammonia, and this liquid ammonia is dilute, not very much concentrated, so dilute solution of this. So basically this metal dissolves in this, so metal dissolve in the dilute ammonia, right? So and different metals have different solubility as well, like lithium has approximate 10.9 so grams per 100 gram of ammonia. Similarly, sodium has 25.1 grams. So and potassium. So down the group, this at low temperature basically this increases solubility, right? So solubility of first group metals down the group increases, but even at low temperature at 0 degrees Celsius also they show the solubility. right? What is the consequence of this solvated electron? Due to this solvated electron, due to solvated electrons, the color of this solution, the color of this solution is blue. Brilliant blue color solution you will get. So the presence of this blue color solution indicates that there is a solvated electron in this, right? What will happen if you take pure metal, pure state metal, and with the high concentration of ammonia, like 3 molar or more concentration of ammonia, if you increase approximately 3 molar, so what you will get? So you will get copper bronze color, right? Or that is metal ion clusters, due to the formation of metal ion clusters. So we will get what? Copper bronze color due to the formation of metal ion cluster, right? Metal ion cluster is formed. Okay, and you know, this blue color solution or this bronze color solution, with time this color disappear and finally this will form the amide and hydrogen, right? And what other properties will change due to this solvated electron? So this conducts, the solution conducts electricity, and the conduction is even greater than any salt solution, right? Conduction is greater than any salt solution, right? That is equivalent to metal conductors, right? And second important property of this, that this solution acts as a good reducing agent, good and powerful, you can say powerful reducing agent, right? See, many of benzene ring, which all of you are knowing that they are resist to reduction, so they can be reduced to, this is aromatic, but sodium in liquid ammonia, if you take, so this will convert into non-aromatic compound like this, non-aromatic compound, right? So the solution of metal in liquid ammonia, they are very good reducing agent, very powerful reducing agent that has ability to reduce even aromatic system to non-aromatic system, as all of you are knowing that aromatic systems are very much resistant for the reduction, right? And one more important point, that some of the metals are also reduced with this sodium and liquid ammonia, and they form even lower oxidation state. For example, if you take bismuth, so with sodium and liquid ammonia, you will have Na3 BI, right? So what is the oxidation state of bismuth here? Bismuth is -3, right? So you can imagine that how a powerful reducing agent is this, right? Similarly, if you take sulfur plus sodium in liquid ammonia, so you will get Na2S, right? -2. Similarly, if you take NiCN4, 2 minus, and if you take Na liquid ammonia, so here you will get NiCN6, 4 minus, right? So what is the change in the oxidation state? No, not 6, 4. CN4, right? So this becomes 0 oxidation state here, +2. So see how this oxidation state of these elements is changing in this reduction process. So this is a very powerful reducing agent, right? Good. Now see the question arises that only first group metal will show such type of behavior in liquid ammonia or some other also. So you know, all first group, you can consider all first group or group 1 metal, show this property that in dilute ammonia brilliant blue color you will observe, and with concentrated ammonia copper bronze color you will get. In the second group you will have calcium, strontium and barium. Group 2, calcium, strontium and barium. They have this tendency. Basically this depends on the ionization energy. So as you know that down the group ionization energy decreases. So in the group 2, if you move from beryllium to calcium, ionization energy decreases. So you will get this type of property also with group 2 metals, but lesser extent compared to the group 1. All group 1 metals in the group 2 you will have this property for calcium, strontium and barium, and a few lanthanides like U lanthanides, like EU and YB have ability to show this type of phenomena, right? Means they dissolve in the liquid ammonia, right? Clear? Okay, now the last point of this group, I would like to discuss some of the properties of lithium, which is very important and something different from the this group elements, means group 1 elements, as well as have some similarity with the group 2 element magnesium, which is popularly known as diagonal relationship, right? So this is some I can put this in a separate note and a special note right here. So this is the last point of our general discussion of group 1, right? First point, that the melting and boiling point of lithium compounds are higher than those of group 1 elements. So melting point and boiling point of lithium are higher than the compounds of other elements, of same group, right? So in the same group, if you compare the melting point and boiling point. So you will find that for lithium compounds it is higher than sodium, potassium and other element compounds. Now the second point is lithium is much harder than other group 1 elements. It is harder than other group 1 elements, right? Third point is that lithium reacts least readily with oxygen, right? Very less reaction, and it has tendency to form normal oxide. All of you are knowing, I have already discussed this, so I am leaving this point. Lithium hydroxide is least basic. As you know, the basic strength down the group increases. Already I have discussed this. So also I am leaving this. And you know, lithium compounds, lithium salts are thermally unstable. Right? Already discussed this point, but just revision. So lithium salts are thermally less stable than other group 1 metal salts, right? So salts and hydroxides all are thermally less stable. Clear? Few exceptions are there, like I have already discussed all these points, like fluorides. So I am taking only the point of difference which I have not discussed yet. Fourth point, we can it is also I have discussed that only lithium has ability to form nitride in the first group, and other elements of the first group, they will not form nitride. So lithium only in group 1 forms nitride. And what about group 2? Group 2 all elements form nitride, right? Group 2 elements forms nitride. Okay. Now the next point is lithium reacts with carbon to form ionic carbide, right? And other group 1 element they do not directly reacts with carbon. So lithium direct reaction, it is important. The formation of carbide, every element form in this group will form, but not with a direct reaction. So lithium direct combines with carbon and form ionic carbide, right? Lithium only in group 1, right? Other sodium, it also forms carbide, sodium acetylide and other similar compounds, but you know, that is indirect, not directly with carbon. Okay. Lithium carbonate, phosphate and fluorides all are insoluble in water. Remember, lithium fluoride, lithium carbonate, lithium phosphate, all are insoluble in water. All insoluble in water, right? And lithium hydroxide, this is sparingly soluble, not very much soluble. Is sparingly soluble. So lithium hydroxide, this is sparingly soluble. So means this shows that this lithium compounds have sufficient covalent character, right? High degree of we can say covalent character. This shows that lithium compounds, lithium and magnesium compounds, basically compounds have sufficient covalent character or covalent character, covalent character, right? So this is these are the some important compounds. Lithium, and sodium compounds, ions, they are heavily hydrated, as I have already discussed, due to their small size. Very few are potassium salts, hydrated salt you will get, but rubidium, cesium do not form the hydrated salt. So this is all about this your first group metal general discussion, right? Now I will start second group. So see, in the second group, group 2, this is called alkaline earth metal. Earth metal group, alkaline earth metal, which constitutes beryllium, magnesium, calcium, strontium and barium. So this is the, and general electronic configuration is NS2. This is the general electronic configuration, right? All are metals and all are good metals, but have less metallic character than group 1. But you can say second most metallic elements are all these are, right? Okay. Well, so see, in this case I have missed one important property, that see, this solution is, this dissolvated electron color is blue, and this solution is paramagnetic, basically, because unpaired electron is there. All of you are knowing, but sometimes you miss, right? So it is always better to write this is paramagnetic. But if you take this high concentration of this due to the formation of this metal cluster ion, and this becomes what? Diamagnetic. Diamagnetic. So this is important. Okay, so let's discuss one by one properties of this second group, group 2, alkaline earth metals, right? General electronic configuration is this. Valency is +2, and oxidation state also +2, and this is fixed. Means there is no variation, you can take it as a fixed value. And okay, that some of the elements of this group have ability to form the covalent compounds, that is a different issue, right? So general electronic configuration, valency, oxidation state. Now the next property is I'm taking here ionization energy. That is important property, ionization energy. So see, ionization energy has the very regular pattern, and it is decreases, ionization energy is decreases down the group. But one very important observation is here, that IE1, if we compare, so IE1 of group 2 is more than IE1 of group 1. Whatever corresponding, you can take in the period, suppose that if you are taking lithium and beryllium, so you consider lithium, compare lithium with beryllium, sodium with magnesium. So IE1 of this group 1 metals, it is smaller than IE1 of group 2, right? It is clear. But remember, IE2 of alkali metals, it is much larger than IE2 of group 2. So IE2, if you are comparing IE2 of group 2, it is less than the IE2 of group 1. Okay, so this all depends on the electronic configuration and size. So two factors are here important to decide this. So electronic configuration and size, all of you are knowing this in the periodic table and periodic properties, right? So left to right size decreases, effective nuclear charge increases, so you can very easily correlate this ionization energy, right? Now atomic and ionic radii. Atomic and ionic radii, so the same trend, you have the same trend, like if you compare Be2 plus, Mg2 plus, calcium 2 plus, strontium 2 plus and barium 2 plus. If it is in the gaseous phase, so this is largest, right? This is the order of ionic radii. Right? But if you take in aqueous medium, so Be2 plus aqueous, this is largest in size, then Mg2 plus aqueous, then Ca2 plus aqueous, then Sr2 plus aqueous, then Ba2 plus aqueous, right? So this is the order of hydrated ionic radii. So you should clear to your question when you are doing question, you should be careful, extra careful, that in which medium it is asked, it is in aqueous medium or it is in gaseous state. If nothing is mentioned, then basically you have to take gaseous state, right? Only if the term is question is asked, okay, arrange them in the order of their radii, right? So radii means it is in gaseous state. And one more property is associated with this, that is the electrical conductivity. So if we are talking about the conductivity, so conductivity depends on the size of hydrated ionic radii. If other parameters are same, so in the same group, if we are talking about in the same group, so magnitude of charge is same, the main difference in the size, so you can relate this. This is very, very important point. So which one has the highest molar conductance, which is the smallest size, because conductivity is inversely proportional to the size in aqueous medium, ionic size in aqueous medium, right? So the conductivity, you will have beryllium 2 plus, Mg2 plus, aqueous, Ca2 plus aqueous, and barium. Strontium 2 plus aqueous and barium 2 plus aqueous. So the conductivity is this, right? Because this is the smallest in size and this is the largest in size. Hopefully it is clear to all of you. Similarly, in the first group also, if you are talking about group 1 metal conductivity, so if you take Li plus aqueous, Na plus aqueous, K plus aqueous, Rb plus aqueous, Cs plus aqueous, so the molar conductivity for this is highest, right? So this is the order of molar conductivity. Molar conductivity, right? So order of molar conductivity for group 2 and group 1 both. Clear to everyone? Okay, you can note down, this is very important point. Metallic character, all of you are knowing that the metallic character, due to very less ionization energy, all are good metals. So metallic character in the group, down the group, metallic character increases, but they are poor metal or have less metallic character than the alkali metal groups, right? So if we take up the next property, that is the metallic character. Metallic character. So metallic character increases down the group, and less metallic than group 1. They are less electropositive or less metallic or less electropositive than group 1 metals, right? So in this group, the strongest metal you have barium. So order if you want, so you can arrange like this: beryllium, magnesium, calcium, strontium, and then barium, right? So this is the metallic character. Now the next property we can take photoelectric effect. So all of you are knowing that in the photoelectric effect, the work function is very important. So work function for them is second group metals, that is more than for the group 1 metals, right? So compared to the group 1, they are not good metal to use in the photoelectric for the photoelectric purpose, but you can use these metals are as a photoelectric for the photoelectric purpose, right? So now the next property is density. So in the density, if you see here, a lot of variation is there in the density of these elements. So if you see, barium has the highest density in this group. After that we'll have strontium, then calcium, and then magnesium, and calcium has less density. So there is no regular pattern, although it is increases down the group, but barium has the highest density. After barium we have strontium. After strontium we have beryllium. See, 1.85 this, and after that magnesium, and then we have calcium, right? So if I would like to write the value, 3.62, 2.63, and beryllium is 1.85, and magnesium is 1.74, and calcium is 1.55. So this is important. Here calcium has the least density, right? So density of calcium is very, very less. All are silvery white, like first group metals. Okay, so density is varies in this order. There is no regular pattern. Highest density is for barium. Okay, it is okay, but here see beryllium is in between. So down the group it is increases, but no such regular pattern, right? Now see hardness. If we are talking about hardness, so all metals are relatively soft but harder than alkali metals, right? So all are soft metal, but uh, harder than group 1 metals. So degree of hardness basically is more for second group metals compared to the group 1 metals, right? Now see, all are soft metal but harder than group 1, and if you compare in the same group, so you will find that beryllium is the hardest, because the enthalpy of atomization is highest for beryllium. After that you will have calcium, then barium, and then strontium, and then magnesium. This is the enthalpy of atomization. Order. So this is in the same group. Now see, melting point and boiling point, no regular pattern is there. Although they have low melting point, low boiling point, but they have higher than the corresponding group 1. So group 2 metals have higher melting point and boiling point compared to group 1 metals. And in the same group, if we compare, so the order of melting point is beryllium, then calcium, then strontium, then barium, and then magnesium. And boiling point order also have no regular pattern, but you will find that beryllium is highest and magnesium is lowest, right? So beryllium, after barium, then calcium, strontium, and magnesium. So you can see here that these two are fixed, means magnesium is the lowest and beryllium is the highest. This is the and calcium, strontium, barium, calcium, strontium, they were changing, right? So this is the melting point and boiling point of this group metals. Metallic character we have already discussed, that is increases down the group, right? Now see, let's discuss one by one chemical properties, chemical reactivity. So first I am taking action with oxygen and nitrogen, means action of air. Air means O2 and N2 both, right? So see, beryllium and magnesium, first important point of this is that beryllium and magnesium Mg are kinetically inert, because inert word itself indicator that it is we are talking about its what kinetic term, because inert is in means kinetic term. Inert towards oxygen, due to the formation of oxide layer, oxide layer at the surface, right? And however, if you take amorphous beryllium, so this reacts with oxygen and forms what? Normal oxide. So beryllium plus oxygen, O2. So this will strongly heated, but amorphous beryllium you should take. So you will have BeO, and you know BeO, this is amphoteric oxide, right? And if you take beryllium plus nitrogen, so on heating you will have Be3N2, right? So magnesium, in the similar way, magnesium also forms the oxide and nitrite. Magnesium plus O2, MgO, right? Heat is required, and magnesium ribbon burns in nitrogen brilliantly, so Mg3N2, right? And this is basic oxide, this is not amphoteric. So beryllium and magnesium. So and similar property with lithium also, because this same reaction we will have with lithium, as you know that lithium and magnesium have their diagonal relationship, right? And if we see calcium, strontium and barium are readily attacked by air to form oxide and nitride, means if we talk about calcium, strontium and barium, they readily or quickly reacts with air. Air means O2 and N2 to form corresponding oxide and nitrite, right? So all they reacts with air, means with oxygen and nitrogen, and forms corresponding oxide and nitrite. All they reacts, right? And this down the group, if you consider the peroxides are also formed, and the barium gives barium peroxide, stable barium peroxide and barium oxide both, right? But calcium and strontium do not have stable peroxide, so barium forms stable peroxide as well. Barium forms stable peroxide also, right? And these peroxides are usually colored due to the lattice defect. Usually colored due to lattice defect. Right? So barium here forms the peroxides, and strontium also form but very little. Calcium do not. Strontium also forms, but not as much as barium, right? So strontium and barium both we can write here. Barium and strontium forms stable peroxide also, but the maximum we will have with relatively, if we talk about, so barium is have more stable peroxide than strontium, right? And one more important property here we have, that beryllium oxide and magnesium oxide, they are used in refractories, used as refractory because they have very high melting point, due to high melting point and good conductor of heat. Good conductor of heat, right? Because since they are good conductor of heat, that's why inner lining of this furnaces we can use to for coating of the inner surface of the furnace, we are using this beryllium oxide and magnesium oxide. This is very, very important property, right? They are good conductor of heat, as well as they have high melting, very high melting point, right? So if you want to see the melting point of this beryllium oxide and magnesium oxide, so I think it is more than 2500 degrees Celsius, or even more, right? Or even more. So yes, so beryllium oxide has 2500 degrees Celsius. Yes, this is melting point is 2500 degrees Celsius, and this has 2800 degrees Celsius, right? So high melting point and boiling point, and they are good conductor of heat, and chemically inert, and electrically insulator. So all these properties, good conductor of heat, high melting point, we can add more properties. High melting point, good conductor of heat, electrically insulator, insulator, and low vapor pressure. So this makes these compounds a good refractory material, right? A good refractory material. Okay, so hopefully all of you are clear of the reaction of oxygen and nitrogen with the second group metals.